Welcome, and thank you very much for joining us today. My name is Fernando Rico. I'm in charge of sales along with my partners in the US for FOTRIC. We're a manufacturer of thermal cameras for a wide variety of applications. And today we're here with Abhishek Menon, who has been using infrared imaging as one of the many tools for his research. Today's webinar is titled Developing a Monolithic 3D Fused Silica Blade Trap for Quantum Simulation with Heavy Ionic Species. That's a long title. And I would like, without further ado, to welcome him. Abhishek, thank you very much for being our guest speaker today.
Thank you. Thank you. Shall I go ahead and share my screen?
Please, yeah,
Yeah, okay. Okay. Is it visible?
it's loading. I'll let you know when it's ready.
Okay. All right. Okay. Can you see my screen?
Yes,
Okay,
we're ready.
perfect. So thank you all so much. Thank you for the organizers for giving me this opportunity to present our work on developing a monolithic 3D fused silica ion trap. And this is a multi-year effort that is between academia, Rice University and Duke University, and industry, Translumic. And only recently we put our work on the archive, having some really significant results on developing a high performance iron trap. And the archive link is here. You can scan the QR code here as well. So, okay, now let's get started. So first, let me get down to the basics and have a more broad introduction. So, what is a qubit? So in classical computers, we know that information is stored in zeros and ones, bits, but they can be either only zero or one. But in a qubit, you can have it in a superposition of two states. And usually they are encoded in a variety of devices which can operate in the quantum regime, such as superconducting qubits or trapped ions, neutral atoms, etc., etc. They all are encoded in the energy levels in those type of architectures. And the essence is that you can store it in this type of complex superposition of two eigenstates. And the characteristic timescales that we look for is how long you can maintain those two energy levels at the required population ratio, and that time of how long it stays there, which is the relaxation time is T1. And then when you maintain the superposition, there is also an effective coherence term associated with it, and that decays as T2. That tells you how much you can make use of the coherent properties, which is being able to interfere the superpositions of multiple qubits when you do multiple linking operations, which we call as entanglement for the quantum regime. And yeah, that gives you an idea of like what is the coherence timescales. So each qubit has its own characteristic timescale for that. So for trapped ions, we encode it in either ground state energy levels or some optical separated energy levels. And the other thing is the trapped is using these RF potentials, and you get a harmonic oscillator as an auxiliary degree of freedom. And so what you effectively have is not only the spin, but you also have a boson or phonon as such. And that makes it a richer type of platform because you can host a lot of new physics associated with it, not only like spin-based simulation models, but you can also have spin boson type of simulations, which are really interesting. So, what is the current status of trapped ions? Well, it's actually one of the leaders in quantum technologies, including for applications in quantum computing, simulation, networking, and metrology. And some of the main features that have been demonstrated in trapped ions is having a very long quantum memory, which is like having a long T2 time, the coherence time. And they've also demonstrated very high fidelity single and two qubit gates, which are responsible for all the quantum algorithms that you want to perform, and also for analog type of simulation. And to even they demonstrate very high fidelity for measuring the population in the zero or the one state. And that is because of all the new techniques that have been developed over the past few years. So we have these ions, but the ions themselves have one part which is completely based on the atomic structure, and the other part which is based on the trap that we manufacture, we engineer. So the goal here is like, okay, how can we make a really good trap so that this harmonic oscillator has can demonstrate a very long coherence time and effectively a very long relaxation time too. Okay, so let's start with how the trap operates. And so the trap that we'll be discussing is the Paul trap. Isolated charges cannot be confined with just purely static electric fields, and that's given by Gauss's law. So named after Wolfgang Paul, who developed this. We have this type of trap which has an oscillating quadrupole potential where you have like RF, RF, and then DC, DC electrodes. And this creates an effective quantum-motive force and which creates this pseudo potential. And that along with electrostatic fields, you can three-dimensionally confine an ion to a almost a single point in free space. So yeah, here is how an animation of how that potential looks like. Okay, and when you drive it at this RF, there is also a little bit of driven motion that the ion feels in addition to the pseudo potential, and that is called micromotion, and that's the little wiggles that you see on top of the more sinusoidal wiggles that you see here. And there are many types of fall traps. The most basic one is the four-rod trap, which is like here you're seeing like stainless steel rods, and it's a very giant macroscopic trap. But from that point, we have evolved a lot to miniaturizing it, making it more scalable and more oriented towards targeted applications. So the trap that I showed earlier was is an Innsbruck style trap, the University of Innsbruck, and there they've demonstrated very high fidelity operations using trapped ions and particularly calcium. And so yeah, this is the type of geometry that you're looking at. So you have the RF DC, and then they have also end caps over there in this picture. And here's a picture of like multiple ions that they image inside the trap. And then there's the more scalable approach, which is using a chip trap, and there you have ions just slightly above, maybe at most 100 microns above the surface of the metal. And then there's this relatively new thing, it's within the past 6, 7 years or so, that you have a 3D monolithic trap. And this was developed also in Innsbruck, which allows you to host large 2D ion crystals. And the applications and the variety of monolithic traps have been fairly restricted. So far, it has been primarily oriented towards 2D traps, and they have a more two-dimensional geometry. But it's quite challenging to think about how it would be manufactured in a way that is similar to the Innsbruck style trap, for instance, wherein you have so many degrees of optical access and a lot of other favorable properties in the system as well. So our goal here is to see how can we get all the best properties that's available for the ion traps and be able to optimize the design and parameters associated with it. Okay, so the metrics that we are considering here are the following. So we have the trap depth, which is basically like the depth of the pseudo potential, trap frequency, okay, and then there's this excess micromotion, which is the residual like mini drives that you have on top of the secular trap frequency that is lower than the drive frequency. And then there's the heating rate. The heating rate is associated with electric noise that's coming from either the environment or the surface of the electrodes, which causes the ion to heat up in the harmonic oscillator. And that affects your effective relaxation time and your motional coherence time, as you can see here. And then the other thing we wanted was very high optical access so that we can have all these individual addressing capabilities and being able to have very high photon collection efficiency so that we can have a very good resolution on our ion imaging. Okay, so let's see about different applications and see how we can tailor our trap in a way that perhaps could meet a lot of these applications. So yeah, so for the case of atomic clocks, usually what they need is a very high trap depth. They need a relatively low trap frequency and micromotion because there are many systematic shifts associated with it. And they want also low heating rate, adding to the same cause. The larger motional coherence helps in having long interrogation times, especially when you want to do quantum logic spectroscopy. So for those reasons, they need to be in this regime. And then for quantum simulation and computation, similarly, we need a high depth, we need a high trap frequency because usually will have spectral crowding of the different motional modes. When you have multiple ions, having multiple ions means you have multiple normal modes of motion because of the interaction of the collective confining potential and the Coulomb interactions that's there in between. And then you'll have, yeah, and then you want also less micromotion, low heating rate, and a long motional coherence time, especially when you want to do spin boson type of simulation so that you can preserve the quantum information in the harmonic oscillator for longer and be able to probe it for longer as well. And this high and multi-directional optical access really enables you to get this individual addressing and high photon collection efficiency. And for networking, the main feature is that, okay, you want the collection efficiency as high as possible so that you can increase your entanglement rate and get as many photons as you can. And at the same time, yes, you have another set of parameters that you need for these metrics. So let's orient the trap in a way so that we can meet some target metrics. Let's put some solid numbers here. Let's say we try to achieve 1 electron volt, the trap depth. trap frequency around 2 to 4 megahertz, excess micromotion as much as 10 volt per meter. Okay. And then the heating rate less than 10 quanta per second, which is like 10 quantized energy excitations per second. That's what it means. And then motional coherence of 50 milliseconds. And hopefully, well, let's see if we can get a multi-directional NA. Okay. So in addition to all this, it would be good to also have it scalable so that it's not just one trap that has all these metrics, but it can be reproduced in with high accuracy. And to do this, we want to benchmark it on heavy trapped ions because a lot of these ions, such as ytterbium, barium, lutetium, they're near the state of the art for the performance of like quantum simulation and computation experiments and networking, and also clocks recently. And to trap these heavy ions, because the trap frequency scales as 1 over the mass, you need a very high RF voltage to compensate for it. And high RF voltage, particularly in vacuum, means that you need very good thermal management. And so, for that reason, it's very important that we have a good construct in mind of how we are going to characterize the trap macroscopically before we go into any microscopic characterization. So for the monolithic 3D ion trap, if we are going in this direction, we want to preserve these properties of three-dimensional blade traps, which host very good performance metrics, but then they're not very scalable and they have a larger footprint. And on the other hand, we have these microfabricated chip traps, which have all nice scalable solutions, but not achieving the best as that of the three-dimensional blade traps. And so for that reason, we go towards the direction of building a monolithic 3D ion trap, and that would be what we'll be discussing soon. And let's start with the material choice. So why do we like I said that we chose Fused Silica, right? Okay, so what's the choice behind that? So if you look up all the common materials that's used in ion traps, you'd find, and green here indicates what is the most preferred in terms of the metric here. Okay, you look up the mechanical properties, the electrical properties, and this thermal properties. You'll find that diamond, sapphire, Fused Silica are pretty good, and diamond sapphire is most preferable. Okay, but the thing is, similar to silicon, diamond and sapphire, they are crystalline, and so creating three-dimensional geometries becomes hard if you are using some form of selective laser etching type of technique. And so it makes it just more difficult for you to get three-dimensional geometries which are arbitrary, like what you want. But so for this reason, we moved on to Fused Silica, which still hosts really good properties. And the way we do it is using selective laser etching. How this works is you have this piece of fused silica, you make a stencil basically out of writing tightly focused laser on top of it. And wherever the laser hits the glass, the density effectively reduces, and so and it becomes more prone to being etched out when you put it in this etching solution by a very high selectivity ratio, and like almost 1 is to greater than 100. And then out you get is this silica block, and that we just butter coat it, and with that we are able to manipulate it and put it in the vacuum chamber and then start characterizing and seeing if we can trap or not. So in our trap design, like these are the features that we wanted to include. As I said, we wanted high NA, we wanted to work with high RF voltage. And so for that, we have very good RF DC isolation. And the design was such that you can get up to like 1 electron volt of trap depth. Okay. And the working distance is about 250 microns. And so, yeah, we etch it. Okay, we get the trap at both universities, Rice and Duke, after this collaborative approach in designing the trap. And then we characterize it in the system. And then after we characterize it in the system, depending on the metrics, if it's good or not, we might have to go back to the drawing board, okay, and then reiterate. And so that's why it was an iterative workflow that went past a little more than 3 generations to get where we are. So the first step for the macroscopic characterization was understanding if the thermal heat sinking of the trap was enough or not. So to do this, what we have is we sandwich the trap between pieces of aluminum nitride, so that because aluminum nitride is a very good heat conductor, unlike fused silica, and we put it in the vacuum chamber. We assemble the trap, the electrical wiring and all, and on one side we image using a thermal IR camera, and the other side with a visible camera. And so just like how and that this is where we use the FOTRIC IR, the thermal IR camera. And from this, how do we know if the trap is behaving well or not? Well, we apply high RF through it, and then we observe if there are any hotspots or not. And the way we calibrated it was by looking at the temperature on a hotbed. We just looked at the temperature and compared it when it's purely from a heating source versus the RF-based heating source. And in the other case, we had a direct in vacuum thermocouple to help us validate if the temperature on the ceramics is what we think it is, as read by the IR camera. Okay, yes. And so we just drove the trap at high RF and high vacuum conditions. And so for the thermal management, yeah, so the very first trap that we got when we drove very high power, RF power through it, we saw it glowing at the RF DC trenches. And that was a big red flag. And so we went to investigate further. What we found was that there was also glowing visibly on the other end, on the other side of the chamber. So the fact that okay, so the temperature that the IR camera tells you was not agreeing with, the black body type of radiation that you're seeing on the visible camera. So it was pointing to a combination of probably RF heating and also some dielectric background breakdown. But in vacuum, you have lower threshold because of this vacuum surface flashover. And so for that reason, we resimulated it. Okay, and we found that, okay, the charge density is maximized over those RFDC trenches and then widen those trenches in the new design. And so with that, in the new design, okay, you can see that they're not glowing as much as these RFDC trenches, but then our overall trap stack was not very reproducible in terms of the assembly. So as you can see, there's a sharp gradient that's there from the top to the bottom. And so for that also, we improved it. And this time we added some aluminum layers from the top and bottom so that we can further dissipate the heat more effectively. And all these three pictures, they were taken with effectively about the same RF power for fair comparison. Then here is a video of how the RF heating goes through. This is like one cycle going from 200 to about 680 V peak and then going back down. And then we're just cycling it through. And the most trustworthy measurement here is, of course, on the ceramics because it becomes really hard to validate what is the accurate temperature at these trenches because the pixels are in the order of like 100, 200 microns and so are the trenches. So that's why it becomes really hard for understanding what the source is, and that's why a microscopic investigation was challenging. But we got good results in the Gen 3 trap, and so now we can move on. And just to summarize, the overall thermal management that we have here. So this is an overview of the development and the reduction of hotspots, and we improve the trench design generationally. And this is how it looks like in the CAD model and also in the final implementation with the aluminum and aluminum nitride for better heat sinking. So now we can go into the microscopic characterization of the trap. So here what you see here is like a 99 chain of ytterbium ions. And first thing what we wanted to see was, okay, we have radial trap frequencies. Can we get to 3 megahertz? Yes, we can. And then second was, okay, for long ion chains to reduce the calibration overhead, we wanted to make sure we had a nice uniform radial frequency distribution. And yes, we can get to about less than 0.2% in fractional RMS about these high frequencies because of our geometry. And furthermore, if you compare it with the simulation, ab initio without any fitting parameters, we see very good agreement between the measured frequency values for all these three different traps that we tested as compared to the simulation. So for that reason, it tells us that, okay, Fused Silica is really good in terms of its precision and accuracy, and it's repeatable as well. And the other property we looked into was the excess micromotion. When the ion is displaced from the very center of the trap where the RF fields all intersect and cancel out, it ends up seeing this RF gradient, and that RF gradient enhances the driven motion and those, little wiggles that you were seeing earlier in that GIF. So to minimize that, what we have to do is we have to move the ion using static fields and bring it back to the null point. And so this is what we did. We did it in along the radial direction, and you can see that blue is compensated and orange is uncompensated. But the working point is the center of the trap, at least on the axial direction. That's the x-axis here. So for that reason, whatever residual micromotion that you have at the center is what you have actually. So in our Gen 2 trap, we had considerable micromotion, about 400. But in our Gen 3, 250 and 200 micron, these two are two different ion electrode distances. There's a small variation, but yet we get a very small, low level of axial micromotion, while the radial micromotion could be completely flattened out just by moving the ion around radially. And so this is a good improvement, and it's also showing that it's reproducible, meaning that our trap assembly is robust and can be reproduced in multiple setups. So the next thing is the heating rate. So as I mentioned, external noisy electric fields, they cause the ion to rethermalize to a higher temperature. And how we probe it is by just allowing, after cooling the ion down to its ground state, we just allow it to interact with the environment, is dark time, and then we just probe it through sideband and evolution. And so in the Gen 2 trap, we observed in the order of like 1 to 10 quanta per millisecond of heating rates. That's very high. That's like a very bad lifetime, as you can think about. Like T2 is like 1 over 10 quanta per millisecond. That's already pretty bad. So, but in the Gen 3, after we made some improvements in our cleaning techniques, including ex situ plasma cleaning, we got down to about 1 to 10 quanta per second. So yeah, this is like order of 100 to 1000 reduction. So this is great, means that we get like close to 10 to 100 milliseconds of coherence time, at least in principle. But then that's a technical limitation on how well you can stabilize the system around it. And so we can get these heating rates pretty low, and it follows this type of 1 over omega to the cube type of law for one mode or radial mode, while the other mode has some technical noise, for which reason it has this maxima. Okay, so if we compare these heating rates to other traps by normalizing it and expressing it in terms of surface electric field noise, we have one of the lowest heating rates that's there, and that too at 3 megahertz. And that's the challenging part, which not many systems have. And that's why here we are able to get it with careful techniques. And this is comparable with cryogenic and macroscopic traps. So with this, we can now go on to some coherent manipulation. We can get very high contrast and clean two-level type of oscillations. So carrier is purely the oscillation between the population of the spin. And then the red and blue motional sidebands, they allow you to couple to the harmonic oscillator so that you exchange one phonon as well when you excite the spin. And so even there, we get very good coherence after sideband cooling. Another demonstration that the heating rate does allow you to get such high coherence in the quantum platform. And the other thing was, as I mentioned earlier, this heating rate is supposed to allow very high coherence times, and the coherence times meaning the coherence time between the lowest two, say, rungs of the harmonic oscillator. And so initially, when we just probed it without any decoupling sequence, we got to about only 23 milliseconds for the radial mode with the low heating rate. But then once we did a spin echo for decoupling and getting rid of a slow frequency drift, we found that this dramatically improved, and a coherence went up to 96 milliseconds. Okay, and that is like getting close to the limit of how well you can get, how long you can store your quantum information across the 0 and 1 state of the harmonic oscillator. Okay. And to further demonstrate the capabilities of the system, next thing as proof of principle, we do an entangling operation. So how we entangle ions is usually using this Momus-Sorensen type of interaction, where when the two spins are coupled to the shared bosonic mode, it allows this a perturbative effect to be able to couple the two spins to itself together. And so you have this strong interaction that ends up mediating a perturbative spin-spin interaction. So the spin phonon gets to spin-spin effectively. Okay, and here we demonstrated again with ytterbium ions, which are heavy. So, and what we see are these coherent two-body type of oscillations when we work in one regime, where you have effectively an off-resonant coupling to the spin phonon. For that reason, you're dominated only by the spin-spin coupling. And so you get very coherent oscillations. And in the resonant regime, they are all in about the same time scales, same coupling strengths in a sense. And so that's why you have different distribution. And just comparing the simulation and the measurements, you have like very good agreement. And then we prepared in this resonant regime at the point where you can perform the gate. And the metric to look for is this parity contrast, which tells you what is your fidelity in maximally achieving coherence across the 0, 0 and 1, 1 state that is in the Bell state that we are preparing. And so with spam correction, we can get it up to 99.3 without any level of pulse shaping as such. I would say it's like a modest Bell state fidelity. I mean, with pulse shaping, this can only go higher. And this is just a proof of principle demonstration that even with all these metrics and about the lifetime and the heating rate, you are able to get very high fidelity in quantum logic operations. And let's look back onto our metrics. Did we achieve them? So yes, it seems like we did achieve at least most of them or get very close to them. And this is a big demonstration of how reproducible, scalable, and reliable these monolithic 3D fused silica ion traps are. And they're great for working with heavy ions, and all the engineering that went into the thermal dissipation really helped. And future directions in the lab are, well, we are looking forward to doing some quantum simulation and making use of the nice spin and phonon coherent properties in the trapped ion system. So here we want to simulate some charge and energy transfer models. Another thing we're looking forward to is probing a dissipative phase transition. And we are also, on the technical side, building a new system for hosting 2D ion crystals similar to that in Innsbruck. Okay, and with that, I would like to acknowledge both teams at Rice and at Duke for all their efforts in making all this possible. And thank you all for your time and attention.
Thank you very much, Abhishek. We truly appreciate your time and the sharing of the methodology and the results that you guys are achieving. It's indeed impressive. So, congratulations to you and your team, and thank
Thank
you very
you.
much for sharing with us. Okay, so this is the time where Abhishek will be open to answer any of your questions. We understand that some of you are familiar to the topic of his research, and some others are here because are interested in learning more about how thermal imaging can be used in many different applications. So whichever is the case, down below at the bottom of your window, you will
Okay.
see the chats where you
So,
can put the questions. And if you have any questions for Abhishek, feel free to drop them there. We will forward to them. I'll read them out loud for him so he can answer. We have one question from one of our attendees. First of all, congratulations, good work. And he asked if you guys have tried any other materials like diamond. I believe you mentioned there.
yeah. So we didn't try diamond, but there are groups that have tried it. And so far, from what I know, it's been primarily in wafer stack type of form. And yes, they have achieved really good results. And this was particularly for clock-based operations. I think NIST and maybe also PTB in Germany, they have this type of trap, but not that I'm aware of or anything that's achieved in a completely monolithic structure. Because when you have it in a wafer style trap, sure, you can be really macroscopic, and there you can be a little more forgiving in terms of the tolerances. But then it's not monolithic. And when you want to work with heavy ions, maybe for clock applications, it's great. But when you want to do quantum simulation and networking, you would need to work with shorter ion electrode distances so that you can get a very high trap frequency, particularly for heavy ions like barium, ytterbium. Yeah.
Thank you.
Yeah.
And the follow-up question to that first one is, what are the main criteria used to select the material in applications
Yes.
like the ones you're investigating?
Yeah. Maybe I can go back to the old slide. Let's see. Okay. Okay. So yeah, so this was the primary criteria. So the Young's modulus is so that you can have a very rigid structure. You don't want it fragile. You don't want it to break in vacuum just by applying some amount of stress here and there. The other thing is so in the electrical properties, you have the ionization work function, the ionization threshold and work function. This is to make sure that for a lot of these species, you work with UV light. And if there is some amount of dielectric that's exposed, there's a chance that you can get some ionization out. And a stray charge there is basically a disturbing point for another, for the ion. And so the ion will see it and then it will affect your quantum operations or whatever you're doing. So for that, we want that threshold to be as high as possible, preferably larger than, many times larger than the wavelength that you're operating at. And yeah, the dielectric constant, a lower value, helps in making sure the trap capacitance itself is low, and there's not and it reduces the power demand from the trap. So this is how it scales the power dissipated on the trap. C is like the trap capacitance, so a low dielectric constant reduces the power requirement also for the trap, lesser overhead on the dissipation. And then dielectric strength and VSF, they go pretty much hand in hand, but here the point is, if you have a higher VSF, and VSF stands for vacuum surface flashover, that's the surface equivalent of the dielectric strength, which is effectively a bulk property of the dielectric. And here you want it as high as possible because that would enable you to have very close structures between the RF and DC electrodes so that you can really pack very fine pitch type of geometry, something similar to what chip traps are doing. So yeah, and that allows you to scale up and have like shuttling and loading zones, so on and so forth. So that is always very favorable to be as high as possible. That's why for silicon, it's actually pretty high. As you can see, it's 30 to 100. Tangent loss reduces the amount of dissipation into the material itself, RF dissipation into the material, and that you can see it here. And the thermal conductivity, yes, well, now you're dumping a lot of RF power into this small footprint of an ion trap, and it would be great if all that heat redistributes within itself and can be distributed very nicely to a heatsink. So for that reason, it's better to have something similar to diamond or sapphire, and fused silica is deficient in it. But by having very good thermal interfacing materials like the aluminum nitride we use, we can mitigate it. And the thermal expansion is another great property of fused silica because when you cycle between low and high RF power through and through, you're going through different temperature ranges, and it's good if the thermal structure itself barely expands. And so that's why it's a good choice that was made here. And diamond is also another good choice. So for that reason, yes, diamond sapphire are really good, but it's just that the technology for SLE is still not as mature as that of fused silica. And it's also because of their crystalline structure that makes it a little more challenging.
Okay. Well, thank you very much for the answer. I would like just to do a quick follow-up on that. Is at this point of research and development, the cost of materials considered at all? And does fused silica have any advantage over the sapphire and diamond when it comes to building the systems?
That's a good question.
Or that's something you
Yes,
guys are not
there
thinking
is.
about right now? And it's like
Yeah, that's not
let's get
something
into
we're,
production.
yeah, yeah, exactly. Because I mean, we mainly designed it, and collaborators, Transloom, they're the ones who have this specialized femto-etch process for SLE. I would assume that silica, well, the thing is for silica, you need very high purity as well. So if you have some degree of other ions that's there, it ends up not performing as well as what you think it is, like all these metrics here. So this is
Mhm.
like very high purity. So I'm not sure exactly of what the cost is, but I still would presume that fused silica is a lot cheaper than sapphire and diamond, just from a manufacturing point of view as well. Yeah.
Okay, awesome. Thank you. We have another question. It says, I noticed there are two different windows for both the microscope and infrared. What is the
Mhm.
transmission rate or ratio normally used in your setup?
Yeah. So I remember the zinc selenide being around 63%. The fused silica, well, it was just visible, so we didn't have anything IR through it. And this typically for fused silica, it can be above 90% in transmission. Yeah.
Okay,
Yeah.
awesome. Thank you very much. And I have another question. Did you guys had in consideration the pixel size of the camera you guys were using? I remember you mentioned at some point that
Yeah.
the temperature measurement was probably not fully reliable because the pixel size or the size of the component you guys measuring were around 100 microns. Was that
Yes,
something that
yes.
was considered?
Yeah, so for that, so because of how small it was, we didn't like realize it that it would be that small and it would impact the determination of what would be the actual cause of it and what the most accurate temperature measurement would be. Because for us, most of it was mainly a qualitative measurement, and we wanted to know like if it was just rising as high or not, and if we could still have sufficient uniformity, homogeneity in the thermal distribution or not. So at the time when we used it, it was comparable to the trench gaps, especially. So I think in this picture, yeah, as you can see here, so in the order of 100 to 200 micron was the pixel size for the working distance we had, which was about 150 millimeters. And the trench geometry effectively has a dimension of about a few hundred microns as well. So they were really comparable. And if there was maybe like one particular hotspot that was like much, much more than the other, and it was less than 100 microns, we wouldn't have been able to resolve it as much, and it could have been like averaged out. So for that reason, we were not able to very accurately determine what the temperature was at those spots. And that's why we were also seeing discrepancies in a part of the reason why we were seeing discrepancies in the air imaging temperature and the visible temperature, particularly for the Gen 1 version of the trap.
Okay.
And yeah.
Thank you very much for your answer. I know that you have a tight schedule today, so thank you very much for your time. Thank you so
Sure.
much for sharing.
Sure. Thank
I
you.
would
Thank you
like,
so much for the opportunity.
thank you, Abhishek. I don't know if we were able to see your last slide where we
Oh
could see
yeah.
contact
Yes.
information,
Yes.
and you had a QR code to access one of the papers that has been published
Yes. Yeah.
with the
Here we go.
result of your
Yes.
research.
Mhm.
So for anyone interested, how do they get to that article? Just
Oh,
scanning the QR code?
yeah. Just scan it. Yeah, you can just scan the QR code, or I mean, if you just type monolithic segmented 3D ion trap and archive, it will come up. I guess this is the like only known one right now that would readily come up with this title. Yeah.
Okay, you guys are
Yeah.
pioneers. Congratulations once again.
Thank you. Thank you so much. Good day.
Okay, I would like to invite all of our dear attendees to stay for just 3 more minutes. As you guys see, Abhishek and his team chose FOTRIC cameras as part of one of the many tools they use in their research. And I would like to share with you what are the current latest and newest technologies from FOTRIC. Abhishek, if you allow me to share now my screen, I would like to share with everyone. Thank you. Okay, Abhishek's team decided to use a pistol grip camera that was portable. They could be mounted on tripods, and that allowed them to see what they were working with so they could adjust and see what it was going to be recorded on the computer. At this point today, we have cameras that are designed specifically for R&D applications that also are mountable on specific test benches with screens and very high resolution with lenses that are designed for microscopic applications. So if you guys are interested, if you guys are looking into the use of thermal imaging for thermal management, for qualitative or quantitative thermal analysis, we invite you to get in touch with FOTRIC. There are models like the one on display right now, which are without a screen, with all the power being done on the computer, which allows users to perform task and analysis, research for 24/7, multiple days, and store all that a huge amount of data on the computer to be analyzed, graphed, and plotted after that. In addition to that, the other model that I showed earlier is one of the highest resolution cameras that has ever been built for these type of applications. 1280 by 1024 pixels, compatible with lenses that provide pixel size down to 20 microns. So it enables users to get really down to a very small scale for applications where, like in electronics, where that matters. And being able to see temperature patterns and the direction of heat dissipation or transport or conduction on a specific very small scale components, it is something that can be now achieved with these type of models. The software that comes along with these cameras is free licensed, which also allows multiple researchers within the same team to have access to the data, to analyze it, to export it, and to make that data captured by the camera usable from a team and not just from the person that has the camera in their specific lab. So with that being said, once again, thank you very much for joining us. If you're interested in about learning about more of what FOTRIC does, what Abhishek has done, and how hundreds of other researchers have also used FOTRIC products, you can reach out to us at info@fotric.com. You already have Abhishek's contact information as well. And without any further ado, thank you. Thank you very much for joining us, everyone. Abhishek, thank you.